Main sequence stars. Main sequence stars are stars in the longest and most stable phase of their lives, steadily generating energy by fusing hydrogen into helium within their cores. During this stage, they maintain a delicate balance known as hydrostatic equilibrium, where the inward force of gravity is perfectly counteracted by the outward pressure produced by nuclear fusion. Approximately 90% of all stars in the universe are currently in the main sequence phase, including our own Sun. Main sequence stars can range from just 0.1 to over 200 times the mass of the Sun. They are classified into 7 spectral types based on their mass, temperature, and energy output. O-type stars. O-type stars are the most massive, hottest, and rarest main sequence stars in the universe. With surface temperatures exceeding 30,000 Kelvin, they emit an intense blue light and produce enormous amounts of ultraviolet radiation. Their immense mass causes them to burn through their hydrogen fuel at extraordinary rates, giving them lifespans of only a few million years. O-type stars ultimately end their lives in powerful supernova explosions, leaving behind neutron stars or black holes. B-type stars. B-type stars are slightly less massive and cooler than O-type stars, giving them a bluish-white appearance. Because they are so bright and short-lived, they never wander far from where they were born. They trace out the vibrant spiral arms of galaxies and often cluster together in groups called OB associations. They are primarily responsible for seeding our galaxy with heavier elements, which are essential for rocky planet and life. A-type stars. A-type stars are white or bluish-white stars, with surface temperatures ranging from approximately 7,500 to 10,000 Kelvin. They are considerably more common than O and B-type stars, and are among the easiest stars to observe due to their brightness. Sirius, the brightest star in Earth's night sky, is a classic example of an A-type star. F-type stars serve as a transition between the hotter white stars and the cooler yellow stars. Their surface temperatures range from approximately 6,000 to 7,500 Kelvin. These stars are slightly larger and more massive than the Sun, and possess moderate lifespans. G-type stars. G-type stars are yellow stars, generally range between 5,300 and 6,000 Kelvin. These stars represent an ideal balance of mass, temperature, and longevity, and are considered excellent hosts for planetary systems due to their long-term stability. The Sun is the most famous example of a G-type main sequence star. K-type stars, commonly known as orange dwarfs, are cooler and less massive than G-type stars. These stars are particularly important in the search for extraterrestrial life because they emit significantly less harmful ultraviolet radiation than Sun-like stars, while remaining stable for extraordinarily long periods, often up to 30 billion years. M-type stars. M-type stars are the coolest, smallest, and most abundant main sequence stars in the universe, commonly known as red dwarfs, and emit a dim red glow. Proxima Centauri, the closest star to the solar system, is an example of an M-type red dwarf. Evolved giant stars. Evolved giant stars are massive, aging stars that have exhausted the hydrogen fuel in their cores and expanded significantly in size and luminosity. These stars typically range from about 8 to over 100 solar masses. As they continue to evolve, they ignite progressively heavier elements through a process known as nucleosynthesis, fusing helium into carbon, oxygen, and eventually iron, transforming into some of the largest and brightest objects in the universe. Similar to main sequence stars, evolved giant stars are classified from coolest to hottest stars, including red giants, yellow giants, blue giants, carbon stars, and hypergiants. Since their classification is similar to that of main sequence stars, I will focus on their specific stellar properties instead of explaining each type individually. Carbon stars have surfaces cooler than the Sun's surface because carbon produced in their interiors is carried into the outer atmosphere, where it traps heat and forms dense layers of carbon compounds. However, their cores can still be significantly hotter than the Sun's core, and this is what makes evolved giants stranger. They often pulsate, changing their size, shape, and brightness over time. The largest evolved giants, such as carbon giants and hypergiants, can lose enormous amounts of mass through powerful eruptions and stellar winds. And since they do that, their mass range stays roughly the same as that of main sequence stars. Their cores, however, can be tremendously denser and give rise to some of the largest supernovae in the universe. Stellar remnants. Stellar remnants are the final remains of stars that have exhausted all of their nuclear fuel. Unlike main sequence stars and evolved giants, these objects no longer generate energy through fusion. The type of remnant a star leaves behind depends almost entirely on its original mass. White dwarfs. White dwarfs are the dense, cooling cores left behind by low and medium mass stars, including stars similar to our Sun. Although fusion has completely stopped, the remnant continues glowing for billions of years as it slowly radiates away its remaining heat. Despite being roughly the size of Earth, a white dwarf can contain nearly the entire mass of the original star, making it incredibly dense. However, white dwarf is merely scratching the surface of our universe's limits, neutron stars. When evolved giants shred their surface and undergo supernovae, they leave behind the second most densest thing in our universe. These cores are so dense that electrons and protons are crushed together to form neutrons, creating an object composed almost entirely of tightly packed neutron matter. Although neutron stars contain up to twice the mass of the Sun, they are compressed into spheres only about 20 kilometers across, roughly the size of a large city. Their density is almost impossible to comprehend. A single teaspoon of neutron star material would weigh around 1 billion tons on Earth. Many also rotate at extraordinary speeds, completing several rotations every second. Pulsars are a type of neutron star, but their unique properties warrant a category of their own. Possessing extremely strong magnetic fields and rapid rotation, they act as cosmic particle accelerators, emitting beams of radiation and streams of charged particles at nearly the speed of light. When Earth lies in the path of one of these beams, astronomers observe periodic pulses of radiation. Black hole. Black holes are the most extreme stellar remnants known. They form when stars beyond the neutron star mass range collapse into a point called a singularity, where matter is compressed to unimaginable density and the known laws of physics break down. The conditions inside the singularity remain one of the greatest unsolved mysteries in modern physics. Their gravity is so intense that not even light, the fastest thing in the universe, can escape. Although black holes themselves emit no light, they are often surrounded by accretion disks. These disks consist of gas, dust, and stellar material spiraling inward at enormous speeds. Friction within the disk heats the material to millions of degrees, causing it to glow intensely and making black holes visible indirectly.